Hi everyone, thank you guys for joining. We are Team Europa, and our mission was to have our rendezvous mission was to go to Triton. Here's our team members.
Hi, my name is Tommy Monorath.
I am Ali Ahmed.
I am Roland Nguyen.
And I'm Chris Kamara.
For our mission outline, we'll be going over a mission overview, an introduction, modeling assumptions, technical calculations and analysis, final calculations, and then summary. For the mission overview, we'll be designing a ballistic trajectory to Neptune. The mission's goal is to perform a deeper study of Neptune's largest moon, Triton, by inserting a satellite into a science orbit. We utilize MATLAB, JPL's Horizon System, and Orbital Mechanics for Engineering Students textbook. We'll be using NASA's SLS Block 2 rocket for this mission, and various mission requirements are outlined for our approach to achieving our mission. For mission requirements, we'll be having that the spacecraft shall have a ballistic trajectory that reaches Neptune. It shall launch between the years June 2029 and June 2033, and it shall have the total transfer time be not exceeding 15 years from launch. The spacecraft shall have a dry mass of 1,500 kilograms, and the launch C3 shall not exceed 130 kilometers squared per second squared to fit within the capabilities of the SLS Block 2, and the trajectory shall include at least one planetary flyby. For mission background, Triton is the largest of Neptune's 13 moons. Scientists believe it to be a Kuiper Belt object captured by Neptune's gravity millions of years ago, and it is one of the few bodies in our solar system known to be volcanically active.
Now we're going on to our modeling and assumptions. So just to inform you guys, these are all applicable to all planets and moons from our flybys to our final destination in Triton. Orbit shall be in the same plane, excluding Triton due to its retrograde orbit. Most of the orbits we'll be using shall be circular, shall use the method of patched conic for Earth departure, interplanetary transfer, Neptune, and rendezvous. Triton's position, velocity, and angular momentum will be aligned with the spacecraft's Neptune and periapsis due to arrival. So some of our justifications of what the team has done here is we're excluding Triton due to its retrograde orbit. We're going from a 3D to a 2D for our calculations. For a circular orbit, makes calculations easier without introducing too much error. Although this might introduce more significant errors, hey, it's a good first approximation. For our method patch conics, we're going to reduce problem from multi-body to a two-body problem, just like explained from the 3D to 2D. Simplifications is accurate enough for the preliminary mission design, and then perfect Triton alignment, no SS to Triton's emphasis data relative to Neptune. Software utilized would be MATLAB and JPL Horizon Systems. For our launch vehicle, as I said earlier, we're going to be using the SLS Block 2. The payload capacity is up to 46 tons. Our thrust capacity is 9.5 million pounds for thrust. And then this also uses liquid hydrogen fuel and is mostly built for deep space missions. The engine that SL uses is the RS25. The ISP is 366 at sea level and 452 at vacuum. But we're going to assume that it's going to be around 400 for our mission. Here's our C3 performance for our coefficients for the Block 2. It should be around, as shown by these graphs from JPL, around 33 to 83 to about 85-ish. Here's our timeline of trajectory from Earth, launching from Earth to our Jupiter flyby, and then arrival at Neptune, and our slow departure from there to its moon at Triton.
Okay, now we're going to be getting into our mission execution. We're going to be starting with an Earth transfer launch date of January 27th, 2030. We're going to be having an initial parking orbit of 500 kilometers above Earth's surface with a max C3 of 83.2 kilometers squared per second squared, giving us a V infinity of hyperbolic departure of 9.121 kilometers per second. And we're going to be having a starting payload mass of 6,917 kilograms of propellant. This is going to take us into our second leg of the transfer to Jupiter arrival. We're going to arrive on February 6, 2032, with a total time of flight between Earth and Jupiter of 740 days. Our V in and V outs match at 7.36 kilometers per second. Because of this, we don't have to do any velocity correction, and there's no cost to our delta V in fuel. Our turn angle is 139 degrees with an aiming radius of 9.3 million kilometers and a closest approach to periapsis of 1 million kilometers. From this flyby, we're getting a boost to our delta V of about 12 kilometers per second. And these are the calculations we use to calculate our flyby properties. Using our turn angle from our V in, V out vectors, we are able to cascade and get various flyby properties.
So for our arrival from Jupiter to Neptune, the arrival date from Jupiter to Neptune will be December 5th at 2042. This leg of the mission will have a time of flight of 3,955 days. As you can see from arrival point 1, the first burn is going to be aligned with the periapsis radius of that first transfer orbit. The velocity vectors at point 1 and point 3 are also parallel, and the spacecraft's angular momentum is going to be the same as Triton's angular momentum. The initial burn at Neptune's capture orbit, it will be at a periapsis of 2,000 kilometers, and the cost of the initial insertion will be a delta V of 2.6921 kilometers per second. The time of flight to between point 1 and point 2 will be a total of 5 Triton orbital periods, and the time of flight between point 2 to point 2 to point 3 will be a total of 15 Triton orbital periods. This will give us a final arrival rendezvous date of April 1st, 2043. The cost of this mission, of this section of the capture phase, will be 2 delta V's, of delta V2 of 0.1487 kilometers per second and delta V3 of 1.1778 kilometers per second. This capture time of flight will be a total of 117.5 days and will end with a 100-kilometer circular orbit around Triton. And these are the equations we use for the calculations of the capture orbits and rendezvous. So, the mission ended up being between 2030 and April 1st, 2043. This gave us a total time of flight of 4,812.5 days, and is equivalent to 13 years and 2 months. Our total delta V used on the entire mission was only 4.0185 kilometers per second. Our starting propellant mass was 6,417 kilograms, and the propellant used for transfer was 4,117.12 kilograms. This gives us an excess propellant of 2,240 kilograms, which allows us to extend the mission. So as you can see, we've complied with every single requirement laid out at the beginning, with a final orbital altitude above Triton at 100 kilometers, a launch window that fit within the 2030 to 2033 window at January 27, 2030, a mission transfer time of 13 years, 2 months total, and a spacecraft dry mass of 15,000 kilograms, or 1,500 kilograms. And our launch C3 was 83.2 kilometers squared per second squared, which fits within the capabilities of the SLS Block 2. Our trajectory includes 1 flyby by Jupiter, which aligns with one of the mission requirements. So in sum, the team agreed to launch the spacecraft from Earth, perform 1 flyby by Jupiter, and perform a capture at Neptune with an arrival rendezvous at Triton. We used MATLAB pork chops and restricted the launch dates between 2030 to 2043, and we determined our launch C3 using MATLAB pork chops, with the restriction of C3 being less than 130 kilometers squared per second squared. We made assumptions to reduce the complexity of the problem, and calculated delta V's in a way to minimize delta V's of between Neptune and Triton's arrival in order to preserve as much fuel as possible. And we ended up, and all the calculations of propellants used and can be seen in the appendix. And that is our presentation.